What we're looking for is how everything works. What makes everything work? It has to do with curiosity.
This song is designed and dedicated to James and friends of starting with such ideas that my father would start me on, you can keep chasing these things and find all kinds of stuff. Well, anyway, I wrote the theme, and there was a problem about the theme, which I wrote rather silly at the end. I tried to explain that all I was able to do, of course, was to discover how it felt, what was happening to your stream of consciousness as you fell asleep, under those circumstances that you were watching yourself. Okay? And I pointed out the standard difficulty of introspection is always that if you try to figure out how it happens, you can only figure out how it happens under those circumstances where you're watching yourself, which may or may not be what happens when you're not watching yourself. And so I made some kind of a little poem at the end, finally, about this idea. It said, the poem, the stupid poem, I said the well-known poem, but of course I made the dippy thing up. I said, I wonder why, I wonder why. I wonder why I wonder. I wonder why, I wonder why, I wonder why I wonder. So, that was my theme. So, okay. That's my theme. I didn't even know he was reading my theme until the end. And then he asked, in the theme I said that I thought, by talking to myself, by making words in my head. And he said, how many people think that they think? That's absurd, he said. How many people think that they think by speaking to themselves in the head? Not one of those suckers had the nerve to put up his hand but me. That was he then. At any rate, I got passed on the philosophy on that experience, but something happened as a result. Because I got in the habit of watching it, although there was a certain date that the theme had to be written, I couldn't stop this habit, see, so I would watch all the time. And then I had the terrific experience, discovery, that I was watching my own dream. that this time it wasn't just falling asleep, it was a real dream inside sleep, and the extra mind was watching, okay? And it started out as dreams do. This is an absolutely silly dream, so I have no excuse for this, but that's the way, you all know that's the way dreams are. In the beginning, I'm riding on a freight car or something on the top, and we go under a tunnel, you see, and I have to duck because I might be, and I think, yes, you can feel fear in a dream, okay? Then the next scenes or so, I'm in the car, walking in the car along, you know, the railroad car, and it jerks. And I say, you could get kinesthetic feeling in a dream. You know, you could, oh, you see in color. Many people don't, some people do. I was definitely see the images in color. And then at the end of the car, there was a kind of window, like a store window, you see, and instead of mannequins, there were three beautiful girls.
And the lack of resilience, within the first few seconds, of course it comes back very slowly, but too slow to... Isn't it true then that the temperature, at low temperature, increases the chance of a joint failure?
The low temperature increases the time that will be required for the O-ring to extrude into the gap.
Yes, and presumably...
And that would allow greater erosion on the O-ring. Yes, sir.
Did you have available, there was some kind of a temperature limit then on when you would say a seal was safe? Was there some kind of criterion that if the seal was lower than a certain temperature, we cannot consider it safe enough?
Yes, sir. The data that we had, and as I stated, we're running extensive testing to understand the response of the seal under the specific conditions of 51L. But the data available to us was the procurement specification for the material that says that it will operate from -30 to 500 degrees F, and also a great deal of test data in motors down at temperatures where you can see a difference in the resilience of the seal. For instance, going from 75 degrees down to 50 degrees, you can see that. We had those data available. We had data that was presented on the 27th by Morton Tykal, some test data that indicated a further reduction in the resilience of that if the temperature was down to 20 or 25 degrees. However, it was the judgment that with the resilience that we saw there, the shrinkage of the O-ring, and under the circumstances of the leak check that is done, that at that temperature the O-ring would perform its function. Now the data that we did see is refuted by some other test data, and that is why we're carefully running controlled tests under the specific conditions of 51L to understand the response of that O-ring seal and will it perform its function in that environment.
Of course, after the event, there's a different circumstance, and I'm not really considering that. It's not a fair question. It could be that we didn't notice the circumstance. I just want to know, before the event, from information that was available and understanding that was available, was it fully appreciated everywhere that this seal would become unsatisfactory at some temperature, and was there some sort of a suggestion of a temperature at which the SRB, I guess you call it,
yes,
shouldn't be run?
Yes, sir. There was a suggestion of that. To answer the first question first, the data that was presented, it was the judgment that under the conditions that we would see on launch day, given the configuration that we were in, that the seal would function at that temperature. That was the final judgment. There were data presented, as we have discussed, by Tykal Engineering, that there was a suggestion that possibly the seal shouldn't be operated below any temperature that it had been operated on previous flights.
Thank you. Other questions?
Could I pursue? But I just have to tell you about this interaction. It works like this. I did already say last time, I gave an example of a problem and showed you what an interaction was, and I'll do it again. If an electron wants to go, let's suppose we have a problem where an electron starts here. It's an electron. Now I'm going to use colors. Good. Photons will be blue. Electrons will be black because of that. So hereafter, all the electrons that are moving around in this game are black, and the photons are blue. And the typical idea is that an electron can go from one place to another, and then go from that place to another, and so forth. That at a particular place, a photon always is emitted by an electron, or absorbed by some other electron, or maybe goes on forever out of the system, to be absorbed on the moon, perhaps. Let's say we would like to have a photon absorbed here, at that moment, at that point. And we had an electron that started here, and we want it to end here. So the electron goes from this particular place in space and time to this particular place in space and time, and the photon is supposed to arrive here. One way it can happen is that the electron goes from this point, which I might call point 1, to some other point, what I might call point 4, and finally arrives at point 2. Whereas the photon goes from 4 to point 3. So this would be the typical amplitude. I would draw a picture like this, and I'll tell you how to calculate it. Let's suppose I wanted to calculate the amplitude. Then an electron goes 1 to 3, 1 to 2, and the photon appears at 3. One way this can happen is one way, only one way, is that it goes this particular way, and I'll call that via 4. And you'll see what that means in just a minute. It means the electron goes from 1 to 2 via going through point 4. And the photon appears at 3 coming out of 4. Then the amplitude for this process is the following number, arrow. It's the following. I'll write it all down and you see if you can understand it. The product. Remember how we multiply arrows? We multiply the arrows. These represent arrows. The arrow corresponding to an electron going from 1 to 4, which for some reason I seem to have written these backwards. No, I know. I discovered from experience that to do it the way physicists write it is unnecessary for beginners. It's only a convention, so let's do it the way it looks common sense. We go from 1 to 4. Then the electron goes from 4 to 2. And the photon goes from 4 to 2. 4 to 3. Okay? And there was an interaction. Let's make this nice thing always happen in red. And then we multiply these together. But the rule for multiplication was explained before. They rotate and shrink. So you figure out what each one of these arrows is, and rotate and shrink. So this is nothing but a shrink. It always says when you have an interaction, shrink the amplitude by this factor, 0.098, whatever it is. I don't remember the number. Okay? I can remember the square upside down, but I can't remember the square root. So whenever a photon comes out or in, like this, and you draw this, that's where the C appears, the shrinking, each time you emit or absorb a photon. And the motion of electrons going from place to place is always governed by this, and the photon always by that. And by that way, in that way, you can figure out the amplitude for anything. Because a whole world of electrons and photons, at least, is nothing but these three processes combined in various ways. That's all. It's done. The one point, however, if all I knew was that the electron started here and ended here and the photon ended here, this isn't the right amplitude. Why? And what would you do to do it right? Huh? What? Yes, you don't know where 4 was. This is the arrow if it happened to do it there. but it may have been that number 4 somewhere else. It might have been this point is here, or here, or here, or here. And for each of those points, there's a total amplitude. Those are alternative possibilities. Those amplitudes have to be summed. So we could say, we have to finish this for this particular problem by saying sum on all possible places, locations, and times that I've labeled 4. Sum this. Make this arrow for every place and add them all together. The square of this would be the probability, the square of this mess, would be the probability that if an electron were liberated here and were found later here, that you'd find a photon in the detector over there at that moment. All right? That's a special problem, and that's the answer to it, almost. I have to tell, there are always more diagrams, more pictures, more ways. Because this electron might have emitted a photon which was later absorbed by the same electron later, and all kinds of terrible things, which I now will explain. So let's take another problem. Well, this is a good one, but we'll leave it there, but we can take other ones to show how it's done. Suppose that I talk about what's usually called the scattering of 2 electrons. One starts at a certain moment from some place, and another starts from a moment from another place, and later you find them in 2 other places. And therefore we have an electron that may have got from here to here, and the other one may have got from here to here. Now let's calculate the amplitude for that. Let me call these positions 1, 2, 3, 4. And I'm going to make a few mistakes. I'm going to rush fast, and you're going to have a few mistakes we'll come back and fix. First of all, for this problem, and I'm drawing this line to save the other thing for the blackboard, for this problem the answer is simply E12 times E34. Right? Electron went from 1 to 2, electron went from 3 to 4. Okay? Anything else? Any remarks? Finish. No, not quite. Yes, a photon can go. Not from 1 to 4. But you could have a situation like this. This is the first picture. I haven't got room on the blackboard. I just love to keep this one. Well, let me erase this and make the picture smaller. So this first picture is now redrawn. Here's 1 and 2 and 3 and 4. Now this is now going to be the basis for the second picture. The second picture has a new possibility. That is that the electron went from 1 to 5 and emitted a photon, and the other electron went from 5 to 6 and picked it up. Yes, and what we're asking for now is the amplitude, a new problem, this part of this section, amplitude of electron originally at, electrons at 1 and 2 go to 3 and 4. All right? What's wrong?
No, but isn't time going that way? You mean 1 and 3?
1 and 3 go to 2 and 4?
Yeah.
Of course. You're absolutely right. Electron 1 at 1 and 1 at 3 go respectively to 2 and 4. Okay? Now, this was the first term. That corresponds to this possibility. But this is also a possibility. And for this possibility, I'll write it down. I'm not going to write anymore because you'll see very quickly what that is. You're learning the principle. You're not going to actually calculate these. We don't know the formulas. But this would be things like E51. This was times, you remember, in the normal business of time. Times E25 times E63. How brainy do you have to be to write this down, huh? 46 times, wait a minute, now got to get a blue one. Yes, you do, yes, you do. Times P56 times more, yes, more. More, yes, more. C times C. Anything else? Oh, yes. Sum. All places for 5 and for 6. Okay? Well, you get the principle now. It's, you have all these things happening. You multiply the amplitudes for all the things that are happening. What are those C's? Those are the junctions. For each junction, for each interaction, we have a factor C, or an amplitude C, a Schwinger. And all of these are the amplitudes for the things to do what they have to do. Now, I have some questions for you. One, what about the possibility that this photon simply comes out here instead of going over here and get absorbed? Why don't I add that in? Different event. Got it. We asked for a special event. We started with electrons at 1 and 3. We ended with electrons at 2 and 4, and nothing else. Something else is a different event. If I were asking for the question, we started with electrons at 1 and 3, and we want to have electrons at 2 and 4 and a photon at 17, that's a different problem, and we start all over again. Okay? You learned that because that was worrying you before. Right. Okay? I mean, in our conversations, the half-hour conversations, that was the thing that was bothering. Are we finished? Is this the complete amplitude for this process? No. There are other possibilities that 2 photons go across and so on. And they write down very much more elaborate strings of these things. And adding this all together is a kind of a technical job of some complexity. So as the diagrams, and these are diagrams, they're called Feynman diagrams actually, as these diagrams become more complicated, they were invented by your speaker. As they become more complicated, each one, you see, each diagram represents a term in a sequence of terms. No, actually, they weren't. They get more complicated and there's more calculation needed to compute them. So how can we make any calculations? We got the whole string. We're saved in electricity by the fact that this C is small. And the more C's you have, the more shrinkings you do, each by a tenth.
Take the world from another point of view.